Welcome to the video help with physics problems for Physics 1A. In this video we'll be covering homework set 1 part 1, which is everything under the heading particle motion in one dimension. For 1121 this is questions 1, 2 and the past exam question. For 1131 it's questions 1 to 3 and the past exam question. Problem 1. In this problem, two bodies are dropped from the same height 1 second after the other, and the problem asks us to find when would they be 10 meters apart. A good way to start this problem is to draw a diagram. So let's put height on the vertical axis and time on the horizontal axis. The first body is dropped at time equals 0. And its height is going to be a parabola like this, given by the height is equal to minus a half gt squared. Now the second body is dropped 1 second later. It's also going to follow a parabolic trajectory, so it'll be parallel to this first one, and this has the equation object 2, y2 is equal to minus a half gt dash squared. Now the relationship between these times comes about because one is dropped 1 second after the other. So this is 1 second. So this tells us that t dash is equal to t minus 1. Okay, so we can just substitute this into this formula here. So we've got y1 is equal to minus a half gt squared, and y2 is equal to minus a half gt minus 1 squared. Okay, now the question asks us to find the time, so some time along down like this, where the bodies are 10 meters apart. So this is 10 meters. So we know that 10 is equal to y2 minus y1. So let's substitute in from these equations into this equation. We've got this is equal to minus a half g. We can expand these brackets here. We've got t squared minus 2t plus 1. And then we've got minus y1. So that's plus a half gt squared. Expanding the brackets, we've got minus a half gt squared plus gt minus a half g plus a half gt squared. This term and this term will cancel each other out, giving us 10 is equal to gt minus a half. Okay, so g is equal to 9.8 meters per second. You can look that up on your data sheet. So we've got t minus a half is equal to 10 over 9.8, which is approximately 1. So this is equal to 1, and so t is equal to 1 plus a half, so 1.5 seconds. And that's the answer to this problem. Problem 2. In this problem, we have a lift which is ascending with an acceleration of 1.5 meters per second. There's a bolt in the ceiling that drops, and it starts to drop when the velocity of the lift is equal to 2.0 meters per second. The lift is 3 meters high, so if we measure this relative to the lift shaft, if we take the bottom of the lift is at 0 meters, then the top of the lift is at 3 meters when the bolt starts to fall. Okay, and we're asked to calculate the time of flight of the bolt from the ceiling to the floor. Now this question's a bit complicated because as soon as the bolt starts to drop, it's no longer affected by the acceleration of the lift. However, the floor of the lift is affected by this acceleration. So the floor of the lift is accelerating upwards as the bolt accelerates downwards. So they're going to meet somewhere in between. What we're going to need to do is write down an equation to describe where the bolt is relative to the lift shaft and also where the floor of the lift is relative to the lift shaft. When the displacement of the bolt equals the displacement of the floor, both relative to shaft, then the bolt will be on the floor and that will be the time that we're looking for. Okay, so let's start by writing down the formula for the floor of the lift shaft. It starts at 0 meters, so we can write y of floor is equal to 0. And now at the beginning time, the time when this bolt floors, the lift is moving at 2 meters per second. So that's equal to 2.0 t. And now plus a half at squared. And this acceleration is upwards, it's moving upwards. So that's plus a half times 1.5 times t squared. This gives us the equation of where in the shaft the floor is. Now what we need to do is write down a similar equation for the bolt. So y of bolt, now the initial displacement of the bolt is 3 meters above the floor. So this is 3. The initial velocity of the bolt, well initially it's attached to the lift, so it has the same initial velocity as the lift. So that's 2.0 t. But its acceleration is in the opposite direction. It's down and it's got magnitude g, which is 9.8. So this is minus a half times 9.8 times t squared. And now what we need to do is solve these two equations simultaneously. So we want y floor is equal to y bolt. So we've got 2t plus a half times 1.5, so that's 0.75 t squared, is equal to 3 plus 2t minus 4.9 t squared. These t terms cancel each other out. We can move this over to here, and 4.9 plus 0.75 gives us 5.65. T squared is equal to 3. And solving that on the calculator, we get t is equal to 0.73 seconds. Note that I give it to two significant figures as the velocity of the lift, the displacement and the acceleration, so this was 3.0, were all given to two significant figures. So that's the answer to part A. Part B says the distance that this bolt has fallen relative to the lift shaft. So the lift shaft is here, it's stationary. The bolt started at 3 meters. So in this question, we don't care about that 3 meters. That's the initial displacement, but we want to get rid of it from the equation because that isn't falling relative to the lift shaft. So what we can do is solve this equation, but we get rid of the initial 3 because we're only interested in how far it's fallen. So y bolt fallen is equal to 2t minus a half times 9.8 times t squared. And we've worked out how long it's falling for here. So this is equal to 2 times 0.73 minus a half times 9.8 times 0.73 squared. So this is equal to minus 1.1 meters. Now the minus is because it's fallen. it's moved downwards and the displacement is negative. So it's fallen 1.1 meters relative to the lift shaft. Problem 3. This is for 1131 only. So in this question, we're given the position of a particle moving along the x-axis. It's given by x is equal to v naught over k, 1 minus e to the minus kt. And these two, v naught and k, are constants. In part A of this question, we're asked to plot a graph of this function with x along the vertical axis, so this is x, and t along the horizontal axis, t. So let's consider time 0. At time 0, e to the minus k times 0 is 1, so this is equal to 0, so we've got 1 point there. Now, as t approaches infinity, e to the minus kt approaches 0, so this part can be ignored, and we've got x is equal to v naught over k. So that's going to be an asymptote here. We've got v naught over k, and it approaches that as t goes to infinity. So this is just going to have the normal exponential shape. It's going to look something like that. In part B, we're asked to derive a formula for the velocity. Now, to do this, we need to use the fact that the velocity is equal to the derivative of time. So this, we can write x as v naught on k minus v naught on k e to the minus kt. When we take the derivative of this first term, this is just a constant term, so we get 0. So we've got to just take the derivative of this term. So we've got minus v naught on k times minus k e to the minus kt. That's how we take the derivative of an exponential function. So these k's will cancel out, and these negative signs will cancel out. So we'll have v naught e to the minus kt. And so as time gets really large, this part goes to 0, and so the whole term goes to 0. So it will eventually come to rest. As t goes to infinity, the velocity goes to 0. Part C, you are asked to find the acceleration. Acceleration is equal to dv dt, or we could write as d squared x dt squared. So all we need to do is take the derivative of this. So this is equal to minus k v naught e to the minus kt. Now this part is just the velocity, so we can replace that as minus kv. So the acceleration is in the negative direction, i.e. it's decelerating. It has to decelerate as it starts with an initial velocity v0 and it ends up with a final velocity 0. So that's a way of checking our answer. Part D says that this particular motion is one with variable acceleration. Okay, this isn't a constant, it's changing with time. Give a plausible physical argument explaining how it can take an infinite time to bring to rest a particle that travels a finite distance. Okay, as the force is proportional to the velocity, it means that as it slows, the force or the acceleration, as force and acceleration are related through F equals ma. So as the particle slows, the force acting against it is decreasing. So if that was to happen, the particle would never actually come to a complete stop. However, clearly it's the displacement is approaching some finite value, V0 on K. So it's only travelled a finite distance, but it's never actually slowed down completely to zero. Because up here the contributions are very small, it's going very, very slowly. Past exam question. In this question, there's a scientist next to a very deep well. She drops the stone and measures the time between releasing the stone and hearing the sound it makes when it reaches the bottom. So part 1 asks us to draw a clear displacement time graph for the position of the stone, and on the diagram indicate the depth h of the well and the time t1 taken for the stone to fall to the bottom. Okay, so we'll put the height here. Here's height 0, which is the height where the scientist is, and here's minus h, the height of the well. Along here we'll put time. Here's time 0. Okay, so the scientist drops the stone and it accelerates downwards, and so as it accelerates downwards, that's going to follow a parabolic trajectory like this. And here's the stone hitting the bottom, so this is time t1 here. So this from here to here, this is distance h, which is the height of the well. Part 2 says show your working, relate the depth h to t1 and other relevant constants. Well, the position of that's part 1. Part 2, the position of the stone is given by y is equal to y0 plus v0 t plus a half a t squared. Okay, now we've said that y0, the initial height, is here, is 0, so this is 0. The scientist drops the stone from rest, so this is 0 as well. And so we have y is equal to a half a t squared. Now for this stone, in time t1 it falls a distance h and the acceleration is g, so we have h is equal to minus a half g t1 squared. That's actually minus h because it goes from 0 to minus h, and so we have h is equal to a half g t1 squared, getting rid of our negative signs. Part 3. We're told that the well is in fact 78 meters deep. So h is equal to 78 meters, and we can take g equals 9.8, the standard value for g, and we're asked to calculate g1. That's meters per second, t1. All we need to do is substitute into this formula. So I've got t1 is equal to 2h on g, and then take the square root. So this is 2 times 78 over 9.8, square root of all that. When we do that in the calculator, we get 4.0 seconds. Okay, in part 4, it says on the same displacement time graph, show the sound wave, and it doesn't need to be to scale. Now, sound travels at a constant velocity, unlike the stone which was accelerating. So it's going to have a straight line, and it's going to be traveling back up to the top of the well. So if you have a ruler, use a ruler. Here it is, here's the sound pulse going up. And then taking the speed of sound to be 344 meters per second, So the gradient here is equal to 344 meters per second. Calculate T2, the time taken for the sound to travel from the bottom of the well to reach the scientist at the top. Okay, so if this is T1, this time from here to here is T2. Show T2 on your graph. So we've shown T2 on the graph. Now we need to calculate it. We've got the height of the well, and it's traveling at a constant velocity. So the time is just equal to h over the velocity. So that's 78 over 344, which gives us 0.23 seconds. Okay, part 6, sorry, this was part 5. Part 6 says state the time t between the release of the stone and the arrival of the sound. So that's the distance between here and here. T is equal to T1 plus T2, and it tells us to think carefully about the number of significant figures. All the data in the question, this is 3 significant figures, but this and this are only 2 significant figures, so our answer should only be to 2 significant figures. So we've got 4.0 plus 0.23. Really, we should have kept the extra significant figures here in our calculator, just in case it pushes everything along one. But this is equal to 4.2 seconds.
No.
Okay, part 7. Now the scientist doesn't have a stopwatch or anything, so she's just estimating things, and she uses G as approximately 10. She can only estimate the sound to the nearest second, and she's calculating the depth of the well. So it takes 4 seconds for the sound to get back to her. So she would estimate the depth of the well using the same equation here. She'd get h is equal to 1/2 times 10 times 4 squared. So that's 5 times 16, which is equal to 80 meters. So she'd estimate the depth of the well as 80 meters. Okay, part 8. We're asked to comment on the relative size of the errors of neglecting the time of travel of sound. Okay, so the time of travel was 0.23 seconds. So 0.23 divided by 4 gives us that this is around about a 6% error. So neglecting is around about 6%. In approximating the value of G, so if we substitute 10 in here and compare this, we get 3.9 as opposed to 4. So that's around a 1 or a 2% error. So approximate, it's around about 2%. Or from measurement error, so the measurement error is that she can only measure to the nearest second, so that tells us that it's 4 plus or minus 0.5, and so 0.5 divided by 4, that's a 12.5, a 13% error. So the measurement error is by far the biggest error, followed by neglecting the sound, the time of travel of a sound, and then by approximating G.